Bismillahirrahmanirrahim. Welcome to Instrumentation and Measurement, lecture number 2. Today we will study about the static characteristics of measurement systems, which are range, span, linearity, and non-linearity. The importance of characteristics is for we have to deal with different type of measurement systems, and each element may possess quite different characteristics, and these characteristics may affect the overall performance of the measurement system. So that's why it is important to study the characteristics, but there are different type of characteristics, and they are being categorized in uh, either as a static or dynamic. Within the static categories, they are also called steady state characteristics. So static or steady state characteristics can be of two types. Systematic, like you can represent them by some mathematical equations. Exactly. And then we have statistical characteristics, for which we need data. We have to conduct experiment, or we have to have some repeated data, so that we can have the statistical quality or the characteristic of that thing. The second category, major category, is the dynamic, which is also known as transient state characteristics. We should remember that static characteristics are very important for in case of measurement aspect. From measurement aspect, out of the static and dynamic, static is more important. Just imagine the temperature measurement for a human person. For example, if we are trying to look the temperature for a human, we give some time for the instrument or thermometer to get stabilized, and we don't read the value within the dynamic range. And when after a few seconds, 5, 3 or 4 seconds, when the temperature is static or a steady state, then this is the temperature that we are interested in. But the dynamic is also important. The dynamic is important from the control perspective, because the dynamic characteristics which are related to the transient state, they tell how the things change from one point to the other point, and the controller has to react within this limit. Okay. So in short, the main message is static characteristics are very valuable from the measurement perspective, while the dynamic characteristics are more important from the control perspective. So what we will study in this lecture, we will study the static characteristics, and for the static characteristics, there are two types: the systematic and the statistical. And what we are going to study is the mathematical representation and their role in the design specifications. Let's go through the static definition of the static characteristics, which is also called the steady state characteristics. These are the relationships which may occur between the output and the input of an element. So we have to find out in this graph, for example, what kind of a curve or the line are we going to see. But we have to be careful that in terms of static characteristic, this relationship is the one when the input is changing slowly. When the input is changing slowly or it is constant, then we observe the static characteristics. Systematic characteristics, it is a type of static characteristics, and these are the ones which can be exactly quantified by mathematical terms or the graphical means. And the statistical characteristics are different, and we will discuss them later. Static characteristics, now there will be a list. For example, we have a range, then we have a span, ideal or straight line, linearity, nonlinearity, sensitivity, environmental effects, stresses, resolution, wear and aging, and error bonds. In this lecture, we will explore in detail with all the examples, all these from range, span, linearity, and nonlinearity, up to from 1 to 4 we will explore. So range is the input range of an element is specified by the minimum and maximum values. So there will be a minimum value and maximum value, for which this element will work, and based on these inputs, the element or the sensor or the device will be able to provide a minimum output to the maximum output, corresponding, for example, O min will correspond to I min, O max will correspond to I max. For example, a pressure transducer, it may have an input range from, it may operate from 0 to 10 raised to the power 4 Pascal, and can provide a voltage output output range of current output range of 4 to 20 milliamps. So 4 corresponds to when the pressure is 0, and 20 milliamps corresponds to when the pressure is 10 raised to the power 4. Out of that range, it will then provide us the value. Another example is a thermocouple, where the input range is 100 degrees centigrade to 250 degrees centigrade, and the output range is from 4 to 10 millivolts. So range is basically something which tells us the operating range, that for this input, and this will be the output. Span is basically the span of the input is the calculation from I max minus I min will provide the input span. Similarly, output span will be provided by O max minus O min. So for the pressure transducer, the example that we just saw, recall that this pressure transducer was having,
you are currently the only person in this conference.
Is the input range of from 0 to 10 raised to the power 4 Pascal, and the output range is 4 to 20 milliamps. In the above example, the pressure transducer has an input span of when you subtract 10 raised to the power 4 minus 0, so you will get 10 raised to the power 4 Pascal. So this is the span, and the output span is around 16 milliamps, because this is the subtraction from 20 minus 4, you will get 16 milliamps. This is the input span, this is how you get the input span, and this is how you are going to get the output span. In thermocouple example, the input range,
you are currently the only person in this conference,
span is around 150 degrees centigrade, and the output span is around 6 millivolts. 10 minus 4 is 6 millivolts, and 250 minus 100 is 150. So this is the output span, 6 millivolts, and the input span is 150. Next comes the linearity. We say a system is linear when the relationship between these two is can be represented by a straight line. And for example, this is the minimum point, I min O min, and this is the maximum point, and a straight line is able to represent it well. So ideal straight line will need two more parameters, ki plus a. This is the linear relationship, and the equation of this straight line, or the model of the equation, can be represented by this O minus O min. This is the slope. You can connect it with the intermediate or A level calculation for the slope, in which you this is like y2 minus y1 upon x2 minus x1, the 2 points, and the minimum point is used for the y-intercept. So we have O ideal, which is O ideal or O linear, equals to ki plus a. Be careful that ideal means linear here. Ideal does not every time does not mean that this will be linear. Here the ideal is used for the sake of linearity, but the ideal doesn't mean that always. The ideal means a linear straight line, right? So here, in case of a sensor, we need an ideal. You can say that for the sensors, the ideal relationship should be a straight line, a linear or a straight line, right? So in other cases,
you are currently the only person in this conference.
So k is the ideal straight line slope given by O max minus O min by this formula, and the ideal straight line intercept will be given by O min minus k times I min. So you calculate k from here and then substitute it here to find the a. So there will be two steps when you go for finding a linear model of a sensor. You first find k, then find a, and then use equation 2.2. So this is the relationship. Example number 1, recall the same pressure transducer, and now we will use this pressure transducers to find the mathematical model. To solve this, recall
you are
that
currently the only person in this conference.
And when you apply, when you calculate k and a, you will arrive to our linear equals to 1.6 10 raised to the power minus 3 I plus 4. In another example, linearity example, a sensor resistance changes linearly from 100 ohms to 180 ohms as the temperature changes from 20 degrees to 120 degrees. And we need to find a linear relationship between R and T. So the solution is the output
You
equation
are
is
currently
O
the only
equals to
person in
Ki
this
plus K,
conference.
and the R is here the output is R and input is T, and the y-intercept can be represented by R naught. So R, we can rewrite this equation and we will arrive to R equals to, we can rewrite R equals to KT plus R naught. So step number one, first find the value of K. This way we calculate the value of K. K is 180 minus 100 divided by 120 minus 20, and the value we get, the sensitivity value is 0.8 ohms per degree centigrade. What does it mean? It means that for every 1 degree centigrade change, the resistance will vary 0.8 ohms. If the temperature is increased, the resistance will increase here 0.8 ohms. If the temperature is decreased, the resistance, output resistance will change about 0.8 ohms for every degree change. Next, find out the R naught value. R naught value is the y-intercept A. So O min minus K times I min. So replace the value for K 0.8. Use this minimum value and we arrive to 84. So now we have the linear relationship of R equals to 0.8 T plus 84. So this is the model of this sensor that you can, since you have a mathematical model, so even if you don't have this sensor available to you, you can use LabVIEW, you can use MATLAB to generate or to mimic this sensor value, and you can add some noise to make it realistic. So this can be the mathematical models. Another application is that you can have simulated or soft sensors for your system, and you can generate data for your algorithms by using these mathematical models. Another example is a basic physical property. This is the RTD, in which we first describe that the basic property of a RTD is that the metal, the electric resistivity of the metal changes with the temperature. And we have one RTD here, which is the 100 at 100 degrees. It's at 0 degrees. The resistance is 100 ohms. At 100 degrees, the resistance is 138.5 ohms, and at 200 degrees, the resistance is 175.83. Now we are given 3 points, and the question is find the linear relationship for the between R and T between 100 to 200 degrees centigrade. So for this, there is one point that you directly use these 2 points, 100 to 200, and ignore this point at 0 degrees centigrade. But this is one way. So by using only 2 points, you will arrive to this RT model. RT equals to 0.3733 T plus 1 of 1.17. But my question is, for example, if you try to, if for example, if we this is 2 point, assuming that in 2 point the linear equation line will be like this. But practically, if we see let me draw it again here. For example, it may be, if I try to utilize this point also, the 0 degrees, and this one, the 3 points, if we try to utilize them and try to draw the best, let me change the color and so that we can see it in a better way. And then, for example, if I try to draw there will be one line like this, there will be one line like this. Okay, so the best line, if we try to use some kind of a regression, if we try to use some kind of a regression, if we try to use some kind of regression, in that case, this regression model, we will do it in the, I think after few lectures we will come to this regression analysis. So if we do regression, let me choose another one like this. So in that case, if we use that one, the model can be from like this, the third line equation. So anyway, there are at least more than one ways to arrive to a better model. So this is one model, but it is using only 2 data points. But if you try to use all the 3 data points, then the model will improve and it will extend to other ranges.